Welcome to Study Loop.
Okay, so we know the due to the energy conservation law, the electric potential energy must be equal to the kinetic energy of particles. So therefore, we have kq squared over 2r is equal to 2 times 1/2 mv1 squared. So the distance between the particles is 2r is because the particle has a radius r. And since there are two particles, that means distance between it is 2r, which is the diameter, okay? And the reason why it's 2 times 1/2 mv1 squared here is because there are two particles, and each particle has an kinetic energy, which is about 1/2 mv1 squared, okay? And m is the mass of proton, and v1 is the speed of proton. So therefore, if we do some arrangement here, we eventually have v1 is equal to square root kq squared over 2mr, and k here is the Coulomb constant. So these are the conditions we know from the question. So we know the charge on the proton is 1.6 times 10 to the power negative 19 Coulomb. The mass of proton is 1.67 times 10 to the power negative 27 kilogram. Radius is given as 1.2 times 10 to the power negative 15 meter, and Coulomb constant is 9 times 10 to the power 9 Newton times meter squared per Coulomb square. So therefore, we can determine V1 is just simply equal to square root, let me see, 9 times 10 to the power of 9 Newton times meter square per Coulomb square. And then times 1.6 times 10 to the power negative 19 Coulomb square over 2 times 1.67 times 10 to the power negative 27 kilogram, and then times 1.2 times 10 to the power negative 15 meter. And this will give us the speed of proton is about 7.58 times 10 to the power 6 meter per second. Okay. And for question B, well, we use the same formula, and this is the formula we derived from the last question. But in this case, the case is different because the last case was a proton-proton collision, and in question B, the case is helium-helium collision. So therefore, the charge must be different, and the distance between the helium is different as well, and the mass is different as well. So therefore, we have V2 is equal to square root kq squared over md. So we know Q in this case is 2e, which is 2 times 1.6 times 10 to the power negative 19 Coulomb, which is equal to 3.2 times 10 to the power negative 19 Coulomb. And the mass in this case, it was described in the question, which is 2.99 times the mass of proton. So we have 5 times 10 to the power negative 27 kilogram. And distance was given as 3.5 times 10 to the power negative 15 meter. So therefore, we can determine V2 now. So the speed of helium is about square root 9 times 10 to the power 9 Newton times meter squared per Coulomb square. And then times 3.2 times 10 to the power negative 19 Coulomb. And then we put the square here. And this thing here over 5 times 10 to the power negative 27 kilogram. And then times 3.5 times 10 to the power of negative 15 meter. And this will give us V2 is about 7.26 times 10 to the power 6 meter per second. And for question C, while we know the translational energy or the translational kinetic energy can be equal to 3 over 2 times kT. And the K in this case is the Boltzmann constant, okay? And T is the absolute temperature. So let's look at the first subcase, which is proton-proton collision. Therefore, we have Ke1 is equal to 3 over 2 kT1. So therefore, we have T1 is equal to 2 over 3 times Ke1 over K. And we know the translational kinetic energy can be equal to kinetic energy, which is 1/2 mv1 squared. Therefore, eventually we have T1 is equal to mv1 squared over 3K, okay? And then we know the K, which is the Boltzmann constant, is equal to 1.38 times 10 to the power negative 23 Joule per Kelvin. And V1 we already know from the first question, which is 7.58 times 10 to the power 6 meter per second. So therefore, we can determine the absolute temperature for the case 1. So T1 can be equal to 1.67 times 10 to the power of 10 to the power of negative 27. Oop. Because this is the mass of proton, okay, kilograms. And then times 7.58 times 10 to the power 6 meter per second to the power square, okay, and over 3 times 1.38 times 10 to the power of negative 23 Joule per Kelvin. And this will give us the absolute temperature for the first case is about 2.32 times 10 to the power 9 Kelvin. And let's take a look at the helium-helium collision. So we just use the same formula, and then eventually we know T2 can be equal to 2 over 3 times KE2 over K. And we know KE2 is equal to 1/2 mv2 squared. And the capital M here is the mass of the helium nuclei, okay? So eventually we have T2 is equal to capital M V2 squared over 3K. We know V2 is 7.26 times 10 to the power 6 meter per second. And the mass of helium nuclei is about 5 times 10 to the power negative 27 kilogram. So therefore, we'll have T2 is equal to 5 times 10 to the power of negative 27 kilogram, and then times 7.26 times 10 to the power of 6 meter per second square over 3 times 1.38 times 10 to the power of negative 23 Joule per Kelvin. And this will give us T2 is equal to 6.37 times 10 to the power of 9 Kelvin. So for the last question, well, apparently the temperature we just calculated is way higher than the temperature in the sun's core, okay? So, well, all these calculations we just did was based on the particle's average speed, which means that the distributions of speed will ensure that it is always greater than the average speed with a certain amount, okay? And the energy that was generated by particles ensure that particles can undergo necessary reaction in the sun's case, okay? And these are my answers for this question.